I'm ready to go.
Okay, great.
Thanks.
Well, thank you everybody for being here today. My name is Kazi. So John and I are going to be coordinating or moderating the seminar. Our associate or our interim director typically does that, but he just welcomed the surprise birth of his first grandchild. So very good reason to skip today's seminar. So as a result, I'm going to give the introduction. So we just want to give a giant ESSEC welcome to Professor Juan Lora. Professor Juan Lora is an assistant professor in the Department of Earth and Planetary Sciences at Yale University. His research spans planetary and climate sciences with specific expertise in climate modeling, hydrologic cycles, and climate dynamics. His current particular area of focus includes investigations of the methane cycle of Saturn's moon Titan, atmospheric moisture transport, and atmospheric rivers on Earth, and variability in planetary atmospheres. And one more thing I have to say is that this meeting will be recorded. All right, so thank you, everybody. I'm just going to go ahead and hand it off to Professor Lora.
Okay, thank you, everybody, and thank you very much for the invitation to speak. It's a pleasure to be here. We were just having I was having a few technical issues there, so hopefully this runs smoothly, but please bear with me if not. Let's see, the other thing I wanted to say before we get started is I have no problem in being interrupted, so if you have questions, please speak up. I don't have, that would be fine to have some discussion during. It's hard for me to see if things are being put in the chat, so I think I'd prefer, to hear somebody speak if that's the case. Otherwise, of course, at the end, I'll take questions. Okay, thank you very much. I'm here today to talk to you about basically the work that my research group has been doing, investigating how atmospheric rivers behave in Earth's climate, but not exclusively in the present and into the future, which may be a sort of more normal scope of things, but also in the past. And the point of this is to try to understand basically what the context for ongoing changes in terms of moisture transport in the atmosphere are, in view of anthropogenic warming, and hence the kind of funny title here, where I have changing climates in plural. And the idea here is that I'm going to be looking at a number of different climate states. I will focus on the modern for a little bit, but I'm also going to talk about the last glacial maximum, the last ice age, a little bit about the mid-Holocene, so 10,000 years ago, mid-Holocene, something like 7,000 years ago. And then also a little bit of the last millennium, to give context to ongoing changes. It's a little bit of a buffet, I guess, of topics here. And so I hope that it's more or less clear, but again, I would encourage you to interrupt me if anything comes unclear. All right. So with that, the motivation for this is in large part to understand the behavior of these systems, which I'm going to define in a little bit, in general, because that's interesting, but also from a more practical perspective to try to understand, how we can better address the uncertainty associated with precipitation changes predicted for the future, for the coming century or so. So this is a slide showing two panels from, I think this is the summary report, the IPCC AR6, the recent report, basically showing, of course, that there are projected increases in global land precipitation. So on the left here, hopefully you can see my cursor. There are projected increases in basically all of the scenarios considered relative to the more or less 2020 timeframe, or 20, I don't know exactly, 2010. Anyway, obviously projected increases with a large range in the uncertainty envelope. And then if you look on the right, there are projected increases in particular regions that have high model agreement. So that's what the unhatched regions show. So there is, of course, increases in precipitation that are relatively large at the high latitudes, and of course along the equator, especially in the Pacific. This is associated with the ITCZ, and the large increases in general, one can think of as a global average response to higher temperatures, of course. Because warmer temperatures means the atmosphere holds more water vapor, which then is transported and can rain out. But of course, there are subtleties to that, and the point of showing the slide is that many of the regions in the extratropics, the middle latitude latitudes of the world where large fractions of the population live, actually have low model agreement in this metric, which again is precipitation change, this percentage at the end of this century. So with that, the other let's see. So we'll move another thing to consider is that natural climate variability is another major source of uncertainty beyond unknowns regarding the projections themselves of greenhouse gases, et cetera. And that's a large part of what comprises that uncertainty envelope that I was just mentioning in the previous plot. And so even in something like mid-century, or even in just the next 20 years, according to the IPCC AR6, natural climate variability will be a major source of uncertainty for water cycle projections. And so, again, this is part of the motivation for us. Now, for the middle latitudes, oftentimes, we think about the storm tracks, and a sort of traditional way of looking at the storm tracks is to look at the eddy kinetic energy, so the energy associated with the storms that make up the storm tracks. So what I'm showing here on the left panels is an analysis from a recent paper that on the left shows the wintertime in the northern hemisphere and the wintertime in the southern hemisphere at the top and the bottom of the eddy kinetic energy in these storm tracks as represented by various reanalyses. So in the colors is one of the reanalysis products. The one that looks pretty good is it's ERA 5 for those of you who are interested. The unfilled contours show the average of actually all other reanalysis we looked at, and we looked at 4 modern reanalysis products. The point being that actually the match between all of them is pretty good, and so the storm tracks are where they are, and the reanalyses agree with each other. And of course, there is a strong seasonality to them. In the northern hemisphere, especially, the storm track is much stronger in winter than it is in summer. On the right, we're showing trends in this eddy kinetic energy. Again, as represented by these reanalyses. And so these are recent ongoing trends. And you can see some robust responses, right? I mean, there's, for example, in the North Pacific, in wintertime, there seems to be a strong shift poleward. And there are other regions where the signal is, in fact, quite statistically significant. However, the storm track changes are associated with a number of competing influences, right? And so the main ones that one might mention here are, of course, Arctic amplification, which reduces the temperature gradient in the middle latitudes, and that should act to weaken these storms by reducing baroclinicity. But at the same time, warming of the tropical upper troposphere will increase baroclinicity at higher levels. And so those are competing influences. There's also static stability responses to ongoing climate change. And so actually the response, the ongoing and also future response of storm tracks to climate change are rather uncertain and again, associated with competing influences that are hard to, once you if you account for one, it's pretty clear, but once you add the other one, the net effect can often be of various, of a conflicting sign. And so this is a little bit of an issue. And so the question I'm asking basically is, can we learn anything about what's going to happen in these extratropical latitudes by explicitly considering moisture transport in the atmosphere? And the subset of the moisture transport going on in the atmosphere that I'm interested in is basically made up of atmospheric rivers. And so, one obviously must ask, what exactly are atmospheric rivers? This is a term that is relatively new and hasn't been in use for a huge amount of time, and in some ways can be controversial. But here is basically the definition that is presented in the AMS glossary. Okay, so these are systems of strong moisture transport. So IVT here stands for integrated vapor transport in the atmosphere, that are often associated with frontal systems, associated again with extratropical cyclones. And so in this left view, we are seeing northern hemisphere schematic, where you have a cold front and a warm front here, perhaps. And this increased region of IVT, again, integrated vapor transport, moving sort of northeastward, that is associated with the frontal zone here. And if you then take a cross section of that along this dotted line, that's what's shown on the right. You can see very clearly the frontal zone, the cold front here, and perhaps the region of the warm conveyor belt. And the atmospheric river really is this region near the surface of relatively warm and humid air, associated sometimes with a low-level jet, which comprises a very large flux of moisture because, again, it's humid and there's a low-level jet that's moving air forward. And so, one can ask, and people do ask, are these basically just a subset of extratropical cyclones, or are they even just a type of feature associated with the extratropical cyclones? And that's a perfectly valid question. But of course, the answer is that they are certainly associated with the extratropical cyclones sometimes, but not exclusively. And in particular, they have somewhat independent, not independent, but somewhat separate life cycles. And so this was an animation that unfortunately is no longer an animation because of the technical issues. But the point that I was going to make here is I've on top of this satellite product showing precipitable water, where you very clearly see the atmospheric river sort of coming out of the lower latitudes around Hawaii and making landfall, in this case, in the Pacific Northwest. This is a sort of a classic Pineapple Express atmospheric river, so-called. There is very much a sign of an extratropical cyclone with the low here and the cold, the cold front, the warm front, all this stuff. But in addition, you can see that there's it's a large scale system. And what was nice about the animation, and unfortunately, again, you're going to have to take my word for it, although here's the date, at the top. This is from 2014, February 12th. You can go find this data set. There are many other examples. What the animation was going to show is that this extratropical cyclone moves through, but the atmospheric river remains, and indeed additional extratropical cyclones move through this region where this atmospheric river remains basically stationary, which says that, yes, the two phenomena are related, but there's not a one-to-one coincidence. And in addition, the anticyclonic flow here associated with the subtropical high in this region is quite important for converging moisture into this region between Hawaii and the west coast of the United States. This, of course, is a regional view. Similar things happen in other regions. So atmospheric rivers are a global phenomenon, and the details of what controls their locations and their their behavior and their frequency differ from place to place. But this is kind of this is the type of separation of phenomena, again, that I think illustrates the usefulness in thinking about these. And of course, I should mention, in case it's not clear, this enormous water vapor flux, once it makes landfall, produces copious precipitation, and it does so along the west coast of the United States specifically, and Canada as well, because it interacts with the topography. So there's large amounts of orographic precipitation as the air is forced upwards, right, by those mountains. There are atmospheric rivers in other regions, which is not clear here. But on the east coast of the United States, there are also atmospheric rivers, and the mechanisms that lead to that water raining out are slightly different because, of course, the Appalachians are there, but the interaction with the topography there is quite different. All right, so hopefully that's clear. The next question, of course, is, do we agree on what an atmospheric river is, I guess, really quantitatively? And the answer is not exactly. You will have noticed that the definition that I gave you before the previous slide was qualitative. And I said, in fact, it was kind of loose because, again, these are systems commonly associated with extratropical cyclones, but not always. And there is really no quantitative definition that we can all agree with, although there have been some definitions that many people have used, one of them being IVT, again, integrated vapor transport in the atmosphere, exceeding some value. And that value used to be 250, roughly speaking, kilograms per meter per second. So what I'm showing in this plot is just an example from an analysis that we did. This is using Mera reanalysis data. And these are the ARTMIP catalogs, the so-called ARTMIP catalogs. ARTMIP stands for the Atmospheric River Tracking Method Intercomparison Project. And so this was what it sounded like, an intercomparison project to try to understand how different algorithms developed by various groups around the world to detect atmospheric rivers agree or disagree with each other. And just for reference here, IVT is defined in this way or calculated in this way. So again, there's a component of the flux of moisture that has to do with the winds, and then of course the specific humidity integrated vertically through the atmosphere. Okay, atmospheric rivers really constitute the strong end of these atmospheric moisture transport events. So these are not just individual small blobs of high IVT that could happen anywhere. These are large scale features, and you can see in these two panels actually the different tracking algorithms, or the different identification algorithms, I should say, all more or less agree with each other in identifying these features, right, of high IVT. And the disagreements happen basically at the margins, less so on the flanks and more so at the sort of the beginning and the end of the ARs. And in this case, over land, the algorithms disagree with each other more over land as the atmospheric river is dissipating. But along the flanks, there is quite a lot of agreement. So in fact, the result of this paper was basically to say, when the atmospheric rivers are moderate to intense, actually most people, this is not shocking, most people that looking by eye and also most quantitative, objective algorithms basically agree on what the feature is. But of course, because we're talking about a phenomenon that exists on a spectrum, right? And again, a spectrum where one has to make a definition at some point, much like in detecting anything else in the atmosphere. It's the weak events that are a little bit more complicated, and the events where the IVT is less strong, that makes things rather uncertain. All right, so sorry about that. Move on. Okay, so now the comparison in this case between the atmospheric rivers and sort of that traditional storm track that I was talking about earlier. The atmospheric river tracks, so-called tracks, which is basically an average of where these features are common, occur and of course are related to seasonal pressure systems and storm tracks, again because of their association with extratropical cyclones, right? So on the top here I'm showing, again, focusing on the North Pacific because this is the region that has received a lot of attention. I will move to more global picture soon, but for the moment, bear with me here. In the gray contours, the sea level pressure, and so you can see the Aleutian low. This is the winter half year, so I should say the cold half year. Okay, so the Aleutian low is here, and again that's subtropical high right here. You can see the integrated vapor transport associated with atmospheric rivers. Now, this is after tracking with one algorithm, and the details there aren't too crucial. You can see that there is this flux that's sort of occurring, between the two seasonal pressure systems, where that seasonal sea level pressure gradient is largest. And if I then plot the same thing at the bottom, that's what the blue open contours are showing, basically the same thing as up here as the arrows. As the bluish filled contours, we can basically put a line through where the maximum intensity is, and you get a sense of where the atmospheric river track is, and that's in relation to the eddy kinetic energies, sort of more traditional dry dynamic storm track, shown in red. And you can see again that there is obviously an association, but there is in fact a tilt of one relative to the other, which is associated with the fact that these extratropical cyclones have to actually pick up the moisture from lower latitudes where it exists and train them into these atmospheric rivers. And so that I think that's what's being reflected here. So these, again, this is a way of showing you that these are phenomena that are related, but rather in some ways rather different. Okay. The next thing to say, of course, is with these trackers, we can come up with a climatological atmospheric river frequency, and that's what's shown finally in a more global view here. The frequency basically the number of time steps in this data set during which there was some sort of atmospheric river. And again, this does not give you this type of look doesn't give you information about the intensity of the atmospheric river, but as long as it was detected by the algorithms used to identify it, in this case, a number of different ones, and it's actually the ones that all algorithms agree on that are shown in this plot. But those atmospheric rivers show up and are counted here, and you can see basically there's equivalent atmospheric river tracks to where one might expect the storm tracks. They're a little bit equatorward of the traditional storm tracks, again, because that's where the moisture is, and they're a little bit more tilted in a equator to poleward direction as you go from west to east. But this sort of makes sense and gives you a sense also of where the atmospheric rivers are important for precipitation on land. In particular, I'll point out they terminate rather dramatically in the West Coast, both of North America and less obviously, but still true, South America. And that's again because of the orography that makes them rain out. But they are also very much present on the eastern sides of these continents as well as East Asia. And of course, there is quite a lot of activity over Australia and New Zealand. Okay, so those are the main regions. Let me also point out that there is quite a significant amount of atmospheric river penetration into Northern Europe. That's important as well. All right, so these atmospheric rivers are key contributors to moisture transport. They really are the dominant mechanism of moisture transport because they comprise the extreme events, not extreme necessarily, but the sort of the high-end events of moisture transport in the extratropical atmosphere. So the middle latitudes. And as a result of that integrated vapor transport, again, there's precipitation. And you can see here what that looks like again. In this case, I'm showing you from simulations, but if I showed you this from your analysis, it'd be very similar. So here's atmospheric river, integrated vapor transport, and precipitation. You can see the values, again, agreeing with the plot I showed you just previously. And on the right is the percentage of total precipitation in the colors that ARs produce. And so, in some regions, upwards of 80% of all precipitation occurs within the bounds of the atmospheric rivers. And again, that is mostly true inside of the storm, of the AR tracks that I was just showing. But in some regions, maybe not 80, but 50, 40, 30% delivered in what are actually relatively short bursts. So if you've heard of atmospheric rivers and have this, have thought about this at all or read papers about it, California is often discussed as a place where a single atmospheric river can make or break the water season, right? And so that's the sort of thing we're talking about. And of course, these are transient systems that pass through in a matter of days. The other thing that's shown on the right here in the open contours are the percentage of extreme precipitation, defined as the 99th percentile, contributed. And you don't see values, but these are actually up to 60%. Or sometimes higher in very specific regions. So again, actually, I think I may have said that wrong. That this may be even higher. The point is that it's a significant fraction, if not the vast majority, of extreme events that are delivered by these atmospheric rivers. And so this is another reason why we really want to understand their behavior. Okay. What about transport of energy? I have been talking a lot about moisture transport, which is how these features are defined. That's what sort of differentiates them from looking at more traditional ways of identifying storm tracks, right? Eddy kinetic energy for extratropical cyclones, for example, or something like that, or sea level pressure variance or something like this. Here we've been talking mostly about moisture transport specifically. What about transport of energy in general, though, in these features? And so on the left, I'm showing you the latent heat flux convergence. So this is the convergence of latent heat flux from horizontal transport of, again, latent energy, but of course that's associated with moisture. And you can again sort of see the same regions that were popping up, although with slight enhancements. And you can also see in certain regions where there's significant precipitation, so significant condensation, and therefore latent heating, along regions with mountainous terrains into which these atmospheric rivers, make landfall, right? As I was describing. But there is a number of other interesting features of this compared to the previous. But in addition to that, and of course, it's hard to compare here because I'll mention this explicitly, the units of these two color bars are different, and there's a reason for that, but we won't get into the details too much. But this is the latent heat flux convergence basically through the whole atmosphere. What I'm showing on the right panel is the near surface sensible heat flux convergence. So this is the heat flux, the sensible heat flux, so associated with the temperatures, convergence in atmospheric rivers, but only in the lowest part of the atmosphere, not through the troposphere. And you can see that there are significant amounts of energy transported, again, not associated with the moisture directly. And so that's interesting. And one can then ask the question, I mentioned at the very beginning that these things are usually associated with warm, humid, conveyor belts, basically. What about temperature, just the surface temperature manifestation of these features, or vice versa, I guess? So how do atmospheric rivers impact the near surface temperature? And it turns out that they do at many different timescales. So again, this is, as with the data from before, this is mirror reanalysis, same data set here. We're looking here on the left at the seasonal correlation. Sorry, these got a little chopped up, and so you can't see. But this is wintertime DJF. This is spring in the northern hemisphere, summer in the northern hemisphere, and fall. You can see the correlation coefficient between atmospheric river frequency and mean seasonal temperature through the 40 or so years of the reanalysis data set. And the point is that in the extratropical regions, especially, there are large regions where there is a huge correlation. And by huge, I mean upwards of 0.8 correlation. All of the regions outlined in little black contours are statistically significant, excuse me. And you can see that there's very strong correlation of seasonal mean temperature and AR frequency, meaning places that get more atmospheric river landfalls than normal, let's say, have warmer than normal temperatures. And if you're wondering, yes, this has been detrended in deseasonalized. Okay, so that's the seasonal time scale. On the other extreme, we also looked at the percentage of extreme hourly temperature excursions within atmospheric rivers, and their result is shown here. Now, of course, this is just a correlation. Both of these are just correlations. This is not causal in any way, but still, you see that along these places where which I've defined as the atmospheric river tracts, basically a little bit equator of the storm tracts, there are regions, again, where the percentage of extreme hourly temperature excursions, again, deseason, detrended, is close to 100% inside of ARs, meaning atmospheric rivers and high, warm, anomalously warm surface temperatures are intimately related to each other. And this is true, of course. In this view, you can see sort of the net effect in the regions where they're very common. But this is true even in more polar regions, and even, polar regions in both hemispheres, for example, around the Southern Ocean and even into Antarctica. So this is something that's been looked at. I mean, not this specifically, but the influence of atmospheric rivers on Antarctic ice sheets, and it's really important. But this is I think we think the first quantification of this at a global scale. So the correlations are really striking. And so we looked into this. It turns out that inside of atmospheric rivers, radiative fluxes more or less cancel out. Anomalous, I should say, anomalous radiative fluxes more or less cancel out, meaning incoming insolation is reflected more than usual because atmospheric rivers are cloudy, right? But that's basically compensated for by an increase in long wave radiation reaching the surface, again associated with that cloudiness and also with the increased water vapor in the atmosphere locally. So those two effects kind of cancel out. What I'm showing here is, again, the sensible heat flux and the latent heat flux. But now this is vertical fluxes, turbulent fluxes at the surface. And basically, you can see that there's a mean sensible heat flux, right, which looks like this. Within ARs, the mean looks like this. And the AR anomaly, so again, these are sensible heat fluxes associated with atmospheric rivers, is basically warming the land almost globally, basically everywhere. So everywhere we look, there's, of course, a little bit of noise, and some of these can be perhaps taken with a grain of salt because in some places atmospheric rivers are very, very rare. So we might be sampling, a single event at these really high latitudes, for example. But in the extratropical latitudes specifically, where there are atmospheric rivers, there is higher than normal sensible heat flux into the surface, meaning the surface is being warmed by the atmosphere. And likewise, the latent heat flux is actually positive down in these anomalous regions for the most part. At low latitudes, this is different, but again, low latitudes are a little challenging here because the frequency of atmospheric rivers there is actually both very low and highly dependent on the algorithm that is being used to track them. And so I would take these blue colors a little bit with a grain of salt, although they might indicate the regions where you have evaporation of the water from the surface into the atmosphere and therefore causing cooling of the surface, right? And then the basically vice versa going on at higher latitudes. Okay. So that's basically what's going on in the modern. These are the sort of new things we've been looking at. I'm now going to turn to the kind of distant past, not super distant if you're a paleoclimatologist, but the last glacial maximum, the last ice age, which was around 20,000 years ago. And this is an interesting time for various reasons. And we've been looking at how moisture transport and precipitation behaved in that time, and obviously with a focus on atmospheric rivers. The reason being that because the last glacial maximum was much colder time, I will show you in a second, there were large ice sheets basically covering much of the high latitude northern hemisphere continents. And of course, much lower carbon dioxide. The global mean temperature was something like 5 to 8 degrees lower than present, than modern. And so, or than pre-industrial, so much colder atmosphere. Because of that, you know, the hydrologic cycle was basically less vigorous. Precipitation was lower, again, as a thermodynamic expectation. But as you can see on the left, this is from simulations, of course, with CSM2 in this case. As you can see on the left, there are regions, specific regions where actually precipitation increased on average. And they happen to coincide in many places. Of course, there is a low latitude signal associated with changes in the intertropical convergence zone. And actually, this is somewhat model dependent. But in the higher latitudes, slightly higher latitudes, in the extratropical regions, there are basically all of the places that see atmospheric river activity in the present also saw at the time, in the last glacial maximum, increases in precipitation, again, in these simulations, much colder world. And so this is really interesting. And it turns out that these sort of simulations, of course, have existed for a while. They match pretty well in some of these regions with proxy records. So these are geological proxy records of precipitation, the quantitative ones. And of course, these are associated with some uncertainty. What's shown on the right here is in the circles, the proxy reconstruction of precipitation, of average precipitation at the last glacial maximum. The size of the circle represents how certain or uncertain it was. So the smaller the circle, the less certain. But you can see basically a dipole in this region, which is a rather data-rich region for this time period, because it was quite interesting. This what is now a desert region, basically today, was much wetter in the past, and there were these like large lakes, etc. And there's this dipole where at higher latitudes there's considerable drying. It turns out that these match rather nicely what the simulations show. So again, on the right actually is the ensemble of PMIP3 last glacial maximum simulations compared to the pre-industrial, right? So that's what's shown. But you can see that the match between the two is rather good. So what's going on with atmospheric rivers at this time, given this interesting behavior at these key regions of land in the extratropical regions? Well, here is a result. This is again CSM2 simulation specifically. Now on this right plot, you can actually see the outline in black of where the large land ice sheets were. So this is the Laurentide over North America. And you can see in the thin contours, the unfilled contours, the pre-industrial simulations, atmospheric river frequency. And in the colors, the difference between the last glacial maximum and the pre-industrial control atmospheric river frequency. And you can see basically that, again, in agreement with the colder atmosphere, you have a drier atmosphere and therefore less moisture transport. So actually the frequency of atmospheric rivers decreased for the most part, except in the North Atlantic in the simulation. And in some regions actually where the number of atmospheric rivers is important, like I mentioned, California, it's hard to see here, but basically the change is very close to zero. And so even though in the main track of this AR feature, you have fewer atmospheric rivers, those impacting the very southwest, the numbers are maybe somewhat similar. Okay. An interesting thing that we also were able to look at with these simulations is, again, the connection to temperature here. Atmospheric rivers brought warm temperatures and actually liquid precipitation. So in other words, I'm talking about rain rather than snow, to these large ice sheets at the last glacial maximum. So what I'm showing on the left here is fall. And fall, I've chosen the season of fall because this is when this signal is most striking, but I encourage you to look at the paper, Skinner et al. 2023. This happened in all seasons. Atmospheric rivers brought temperatures to these ice sheets that were anomalous by up to 20 degrees Celsius. And so you can imagine, even in a much colder world, 20-degree temperature excursions often took the surface temperature to above freezing conditions. And again, in addition to that, the percentage of atmospheric river rain and snow over ice sheets was significant. So snow is obviously contributing to the building of these ice sheets, but the rain actually is which is shown in the blue here, and so this is interquartile range and extreme, maximum minima. You can see basically over the Laurentide, for example, something like 50 and in some extreme cases, 70% of atmospheric river precipitation over these ice sheets was made up of rain, liquid precipitation, meaning likely contributing to melting. Although, of course, there could be refreezing, and that's not taken into account. Okay, so in combination, these two effects, so anomalously warm temperatures in atmospheric rivers and this large fractions of precipitation delivered as rain, actually likely contributed to ice sheet melt. And so we're basically positing that that atmospheric rivers may have been an important factor in the retreat of the ice sheets after the last glacial maximum. So what's shown here is the estimated, and this is a pretty simple estimate, but nevertheless something that's important to do. Estimated ice sheet surface mass balance due to atmospheric rivers. So I should emphasize here that this is estimated based on the atmospheric rivers in this equilibrium simulation. We are not here using coupled ice sheet modeling. So that's an obvious step that could be taken in the future. But these results clearly hint that the margins of the ice sheets in particular were probably strongly affected by atmospheric rivers and strongly affected in the negative sense, meaning they were probably causing lots of melt. Okay. I'm not going to really talk about it. In fact, I'm not going to talk about it at all, but there is a recent nice study that came out looking at atmospheric rivers during the deglaciation. And in fact, in specific regions associated with meltwater from melting of ice sheets and slowdown of the North Atlantic meridional overturning circulation, increases in atmospheric river activity over Western North America that again may have brought even warmer and wetter conditions there. All right, fast forwarding 10, 12,000 years, something like this. I'm now looking at the atmospheric river activity during the mid-Holocene period. So this is a time when rather than having large ice sheet and vastly reduced greenhouse gas concentrations, what we had is a different insolation regime because of orbital changes in the orbit of the Earth, right? And so the seasonality was quite different. And so we were curious what the seasonality changes would do to atmospheric river behavior. And what's shown in these two plots is that the Holocene minus control, pre-industrial control precipitation difference shown here. So there's drying in some of these mid-latitude regions on average, was largely contributed by changes in atmospheric river precipitation. In particular, in the Northern Hemisphere, there's basically a shift of the precipitation associated with atmospheric rivers poleward, which caused basically drying of these regions that I've been discussing, but also wetting of more northern regions. And by the way, it's not really shown here, but in this paper, which I of course encourage you to look at again, there's also a vast discussion, a long discussion about the coincidence with proxy records. So again, I think we have these simulations that agree rather nicely with the records that we have, and we are basically linking a lot of the extratropical precipitation changes to atmospheric rivers. All right. The other thing to mention, I failed to mention this previously, but note in particular the magnitude here of the changes. So this is something like on the order of 100 millimeters per year. Turns out that at the last glacial maximum, the changes I was noting were something like on the order of 1 to 2 to maybe 300 millimeters per year. So order 100 millimeters per year of change in precipitation associated with atmospheric rivers. That's going to become important in a bit. All right, so now finally moving forward into the more present. I'm like I mentioned earlier, I'm going to go back a little bit to the last millennium in a bit, but I wanted to talk about some of the results we've gotten for the historical interval and a little bit into the future. Turns out atmospheric river activity did not seem to change very much in the 20th century, despite 1 degree warming, anthropogenic warming, of course. And so these are results from the CSM1 all but one ensemble. So this is in this case, I'm showing just the historical simulation minus internal variability, and we're able to subtract out internal variability because it's an ensemble, right? But in this case, we have all the forcings included. But this CSM1 all but one ensemble allows us to look at the influence of individual forcings. So when I say forcing, in this case, I mean greenhouse gas concentrations, aerosol loading, and other things. The other things turn out to not be so important. But you can see in this picture, basically, the difference between historical trends and the internal variability in atmospheric river activity, which is shown in colors for the AR precipitation, and in arrows for the vapor transport associated with precipitation, you can see that there might be some small trends here and there, but really it's mostly noise and not statistically significant. The reason for that, again, which we can interrogate with this nice ensemble of all but one forcings, is basically compensating effects from aerosols versus greenhouse gases. And so even though the climate warmed by something like 1 degree in this interval, actually the influences on the hydrologic cycle from aerosols versus greenhouse gases was about the same for these extratropical regions at least. And of course, you might think aerosols are sort of heterogeneously distributed, but actually the influence is still more or less global. And the influence is basically drying, less transport by atmospheric rivers and associated less precipitation, basically global. And that's what's shown on the left plot. And if you compare that to the greenhouse gas concentration influence on the right plot, you can see basically equal but opposite effects. And so if you add these two together, this in fact is what accounts for the response, for the non-response of atmospheric rivers during the 20th century. So with the same simulation, what about the future? Well, here's what the future looks like. Future minus historical, again, accounting for natural variability by using the ensemble. In the future, so this is end of 21st century, the changes versus the historical interval are enormous. Note the difference in the color bar here. We have 20 millimeters per month, and again, so that turns out to be a similar magnitude as I was talking about previously, 240, right, at the maximum. So again, order 100 millimeters per year, right? You can see very large increases. So in this case, the greenhouse gas concentrations the influence of greenhouse gases far outweighs any compensating influence from aerosols, and of course that's because aerosol emissions have projected to decrease significantly. And so this suggests again changes in some regions, especially northern Europe in this simulation, in particular in the southern tip of South America, for example, and other regions as well, East Asia, seeing changes in the next 50 to 50 to 60 years or so of comparable magnitude to what we saw from the last glacial maximum through the modern days, or through the pre-industrial. So that's huge changes, and that puts that into context. So I've been mentioning in this last little bit a lot about natural variability. We wanted, of course, to try to understand what controls what the dominant signal of natural variability is for atmospheric rivers. And so we turned here for that exercise to the CESM last millennium ensemble, this so-called LME, which covers more than 1,000 years, with basically all of the forcings that we know existed. Obviously, some are reconstructed better than others, but basically looking at the forcings that have happened through the last 1,000+ years, and examining, again, with a number of different, because it's an ensemble, a number of different realizations, right? We can look at the behavior of atmospheric rivers in these systems and try to understand how variability was controlled. And so what I'm showing in these plots is the regression of atmospheric river frequency in the contours, in the unfilled contours, and atmospheric river precipitation in the colors onto the northern annular mode in the left and the southern annular mode on the right. And so the annular modes, in case you're not familiar, for those of you who may not have heard of them, the annular modes basically just are the dominant mode of extratropical variability in the jet stream. Basically, they describe poleward and equatorward shifts of the jet stream associated with natural variability. And so the positive phase of this mode corresponds to a poleward shifted jet stream, and vice versa. And so doing this regression tells us basically that shifting of the jet stream is in fact a very strong control on the variability of atmospheric rivers. Now, that may not surprise you hugely, given what I've been saying from the beginning, that these atmospheric rivers are phenomena strongly dynamically linked to extratropical cyclones. But again, they're not exclusively linked to extratropical cyclones, and actually most of the investigations of atmospheric river variability have focused on tropical Pacific variability. So El Nino, Southern Oscillation, or the MJO, for example. And so those are important, and they're important especially regionally. But our finding here is that globally, actually, the annular mode, so the dominant mode of extratropical variability, dominates the natural variability of the atmospheric rivers in these simulations. And again, what's nice about having a multi-member ensemble is that we can do this individually for each of the members. And so what I'm showing at the bottom here on the left is the first empirical orthogonal function EOF1 of atmospheric river activity. And you can see this pattern that resembles that at the top, especially in the northern hemisphere. And very importantly, we did it independently for each of the members, right, for this ensemble of 1,000+ year simulations. And every single case, the amplitude of this mode is stable, meaning that this is not just associated with some type of forcing. This is the dominant type of variability in the atmospheric rivers in the last millennium, basically, at least according to this ensemble. And I think this is quite robust because we also checked this against reanalysis. The problem with reanalysis, it's a very short period, but nevertheless, the agreement in the patterns emerges and is really quite dramatic. Okay, so that basically is what we're claiming controls a large fraction of natural variability, and this is what we can account for in the all but one ensembles. Hopefully that is clear. Okay, the very last thing I want to talk about, and then I'm happy to take questions, is coming back to this question of uncertainty associated with detections. We have been leading one of these ARTMIP experiments. And so again, ARTMIP, I mentioned it at the beginning, but I'll say it again. ARTMIP stands for the Atmospheric River Tracking Method Intercomparison Project. It's been a very successful collaboration. Many papers have come out of it. The idea being to try to pin down the uncertainty associated with the identification of atmospheric rivers. Because again, when you have an objective identification method, that carries its own assumptions with it, of course, and in particular with something like atmospheric rivers, where again we're making a decision about how whether or not something is an atmospheric river based on many cases based on thresholds, for example, that can be significant. So what we did in this case, and ARTMIP has a history which I'm not really going to get into, but there we have the reanalysis, we have looked at many other things. In this case, which my group has led, we ran 2 simulations. Again, with CSM1 in this case, one where we have altered seasonality as the only change relative to a pre-industrial control simulation. And so by altered seasonality, I basically mean a Holocene-like simulation, except it's not Holocene-like in any other way, except that the seasonality is different, right? And so we have a stronger seasonal contrast in the Northern Hemisphere. And then another simulation where we have just global cooling, and that's to contrast from global warming, of course. But again, it's a single forcing simulation where the only change was decreased greenhouse gas concentrations. In fact, decreased carbon dioxide concentrations specifically, relative to a pre-industrial control. Everything else was held the same. What I'm showing in these 2 plots is in the open contours show the median AR frequency in the pre-industrial as detected, the average frequency for each algorithm put together. So the median of those is what's shown. Hopefully that's clear. In the open contours, and the colors show the change in that value. So for all these different identification algorithms, I should say, I didn't list them here, unfortunately, but there were, I believe, 12 different identification algorithms included in the study. And you can see in the altered seasonality case, there is a very clear signal of shift northward, right, in the frequency of atmospheric rivers. So decreases in the core of the atmospheric river track and increases poleward in the Northern Hemisphere, in the North Pacific. A hint of that in the South Pacific, and sort of more confusing signals, but perhaps decreases and again, some very slight polar shifts at other longitudes, okay? But signals that are more or less clear in certain places, right? Versus for the global cooling simulation, basically decreases in the activity of atmospheric rivers globally. And of course, this makes sense again because it's a drier atmosphere. By the way, I didn't mention it, but this is the CO2 concentrations basically taken from the last glacial maximum, so compared to what I showed you earlier. But again, in this simulation, we don't have ice sheets or anything like that, different from pre-industrial. Okay, so you see a decrease in the frequency of atmospheric rivers, and in particular, in the North Pacific, you can see a frequency decrease throughout the track of atmospheric rivers, but in the North Atlantic and throughout the Southern Hemisphere, you basically see decreases in activity actually at the flanks of these atmospheric river tracks. So basically, these tracks are contracting in the simulation, right? So, okay, these are results that make some sense, but what's really important is that what we then looked at the interquartile range of that detected atmospheric river frequency by the different algorithms. And you can see very clearly in this plot at the bottom, which shows that interquartile range, that the altered seasonality simulation has much lower uncertainty associated with the different identification algorithms. So again, what the bottom two plots show is how much spread there is basically in the signal associated with how different identification algorithms detect atmospheric rivers. And so what this is saying is in an altered seasonality case, which of course there's slight variations to the background mean climate, but actually an altered seasonality climate, it has something close to a similar mean climate as the pre-industrial, and it's just the seasonality contrasts that are changing, right? In that case, the algorithms seem to agree in how atmospheric rivers change. On the other hand, in a case where we alter the mean climate, the entire climate globally cools, in that case, the algorithms all agree on the sign of the change in algorithms, in atmospheric rivers, but the algorithms don't really agree on the magnitude. And so there's quite a large spread in interquartile range. And the finding here basically is likely many of these identification algorithms are perhaps overtuned. I don't want to overstate that, but are just too closely tied to the modern background mean climate to really give us a robust and confident detection of atmospheric rivers in altered mean climates. Meaning, as we go into the future or as we look to the past in simulations, we have to be very careful with the type of algorithm that is being used to detect atmospheric rivers, because taking care of what the background climate it looks like is probably quite an important thing to do. All right, so with that, I'm going to put up some concluding remarks. I'll talk through these very briefly, but I want to leave time for questions. So again, although atmospheric rivers are only qualitatively defined, they're very important components of the mid-latitude water cycle. They have important impacts beyond precipitation. I talked about temperatures, surface temperatures in particular, and that's not exclusive to high latitudes. That actually is very impactful at mid latitudes as well. So that's something that we're excited about. Atmospheric rivers respond to climate change, as expected in a sense, in thermodynamic sense. Global warming leads to more moisture. Global cooling leads to less moisture in the atmosphere, and therefore atmospheric rivers react to that. But in addition, there are dynamical signals, right? So for example, I didn't talk about this in detail, but for example, the ice sheets cause dynamical changes that basically reroute the atmospheric rivers, or as we just saw, seasonal changes can have impacts. And so the nature of the climate change is important in considering how atmospheric rivers will respond. More specifically, what I've talked about, relative to the pre-industrial control, atmospheric river precipitation at the last glacial maximum since the mid-Holocene and also towards the end of this 21st century, all show signals of very similar magnitude. Again, I mentioned the 100 millimeter per year signals, and that's fascinating. And in fact, this is also the magnitude comparable to that associated with natural variability. So that variability driven by annular modes leads to variations of the same order in terms of precipitation. And so you can take that in a number of different directions, but what we're saying basically is that the changes in the future, at the end of the coming century, actually this century, to be clear, the end of this century, rival the most extreme excursions associated with natural variability in magnitude, and also rival the change associated with going back 10,000 or 20,000 years. So it really is hugely clear signal. Not at all ambiguous in the sense that it's happening. And of course, again, the details of it might be a little bit uncertain, but that is in contrast to what I started with, which is looking at the eddy kinetic energy, which is a little more difficult to pin down. Okay, and then lastly, I mentioned this, annular modes are the dominant driver of this natural global atmospheric river variability. That's not necessarily true regionally, but globally, it's the signal that pops up. And then finally, our ARTMIP experiments really suggest that how detection algorithms account for the background mean climate it really impacts how they the results that they get. And so care must be taken when doing climate change studies with atmospheric river identification methods. Okay, I will leave it there. I'm more than happy to take questions, and thank you very much for listening.
Thank you, Professor Lora. So now we have some time for questions. So if anybody has a question, you should all be able to unmute yourself, or you can raise your hand and I can cue you.
I have a quick question. When
Go ahead.
you were calculating the information about the atmospheric river precipitation from way back in the day, was it based on observations or simulations? How were you able to get the data? That's all I ask.
Yeah, that's a good question. So I hope I mentioned this. Many of the paleoclimate experiments, in fact, all of the paleoclimate experiments are from simulations with climate models. So CESM, the Community Earth System Model version 1 or 2, depending on the study. So these are simulations, and we have information to force them. But we did certainly benchmark all of the simulation output to geological proxy reconstruction. So records of precipitation and other things, temperature, from geological records. And so I hope that answers the question. They're free running equilibrium simulations, but again benchmarked with records.
Is there an opportunity to get more robust records later, and that could be put into your results?
That's a great question. Yeah, we can talk about where those simulations are less robust or perhaps less reliable. And in some of the regions that I mentioned, more records would certainly be helpful to compare against. So one good example is Iberia. So Spain, Portugal. This is a region that I showed has significant signals in terms of atmospheric river precipitation at these timescales, the last glacial maximum in particular. And the records are really not very good there. So yes, absolutely. Better records from that region in terms of both the sign of change in precipitation, of a mean change in precipitation, and certainly the magnitude, and whether there are changes with latitude or longitude in Iberia and elsewhere in Southern Europe, would certainly help us to, at the very least, to better benchmark our simulations, if not to really refine them. I could keep going about this. One of the things that is a big uncertainty in these simulations of the last glacial maximum in particular is the height of the ice sheets. That seems to have a strong effect on the resulting circulation of the atmosphere. And even though we know the outline of the ice sheets rather well, we don't know the height of the ice sheets all that well. And that records like the ones I just mentioned might help us to refine that a little bit if we can find correspondence between the location of precipitation changes and their and the associated circulation and the height of the ice sheet. So I hope that answers the question. It's a very good one. The answer is absolutely yes.
Thank you very much.
Thank you.
So Sarah Tucker had an add-on question to that. I'm just going to read out loud because she said she doesn't have a mic. She said, adding on to the previous question, what sort of observations of ARs in the current climate would help improve these studies?
Yeah, that's a really great question. I think, there's a number of things. One of the other things we did with ARTMIP is to look at the uncertainty associated with reanalysis. So of course, everything I did that is quote unquote observations is really from reanalysis, which is really not observations, right? It's simulating observations, but there is uncertainty. There's a spread associated with the reanalysis product you're using. So for example, I focused a lot on MERA, and MERA is more moist in the atmosphere than many of the other reanalyses. And so that might be something to think about. And so really pinning down, better understanding what moisture transport looks like regionally over some baseline, over some long enough baseline where we can track these features independently in for example, satellite data sets would be ideal. There are enormous reconnaissance studies, especially out of UCSD, that fly planes and drops sondes and stuff like this into atmospheric rivers, and they have they have been very successful at a better, understanding some dynamical features. But again, when you focus specifically on an area, that doesn't give you information about global characteristics. So a lot of that work has been done in the North Pacific, and I think we have really a dearth of information from the Southern Hemisphere. I mean, so that would be an example. Another example is that we've tried we and other groups have tried to identify atmospheric rivers, again, from integrated vapor transport directly from satellite data exclusively. Of course, moisture meaning the specific humidity of the atmosphere is more or less okay to get, but once you have cloudy skies, actually wind vectors are basically impossible. And so a lot of the times we have to fall back on using geostrophic winds for the dynamical component of the IVT. It'd be great to have better winds somehow. And so all of these things certainly would help our understanding of how these features are behaving. And again, I mean, I'm sort of repeating myself here, but more data, more observations, better observations of regions outside, especially of the North Pacific, would be ideal. Not that the North Pacific is not hugely important, it is, but we have basically all of the data. It comes from that region, and we really should understand what is going on more globally. Great question. I hope that wasn't too sprawling an answer.
Thank you. We have any other questions before we wrap up? Okay. Well, unless I am interrupted, we're a couple minutes after 3 now, so I think we can go ahead and close up. So thank you everybody for coming. Thank you so much, Professor Lora, for giving us this great talk. We're going to conclude our series next, or series not forever for the semester next week. So please, everybody, I'm looking forward to seeing you guys all in person for Dr. Dyla Kirschbaum's seminar. Okay, thank you again. Everybody have a great afternoon.
Thank you very much.